When a structural engineer embarks on designing a structure, one of the first steps is the determination of loads or forces that the structure will need to support. Among the many forces that engineers wrestle with, earthquakes pose a unique and thrilling challenge. In this video, we'll dive into the world of seismic engineering and explore how seismic loads differ from other structural forces while at the same time tracing the evolution of seismic design codes. Our goal is to discover and put a spotlight on the philosophy behind the determination of the seismic event or events that form the basis for the determination of seismic forces by structural engineers. Before we get to earthquakes, let's set the stage by exploring the different types of loads that act on structures. Dead loads are the constant, unchanging weights of the structure itself. They include elements such as the concrete or wood floors, steel beams, roof tiles, and other elements used in construction. Dead loads are calculated by summing the weight of all permanent components. In addition to dead loads, we have live loads, which are the dynamic, temporary loads from occupants, furniture, or vehicles. Live loads vary by building use. There are live loads due to direct human occupancy, such as a crowded lecture hall, or live loads due to movable items, as is the case in storage facilities or a parking garage full of cars. Live loads are typically provided prescriptively by the code. Building codes used in the United States provide specific values that account for live loads in different occupancies. In regions where winter brings heavy snowfall, structures must support the weight of accumulated snow. Depending on the magnitude, snow loads required to be used in design in a particular locality are provided by the authority having jurisdiction. All the loads we have considered so far primarily act vertically downwards. Structural designers must also consider forces that act laterally, including wind and seismic forces. Wind typically moves laterally, pushing and pulling structures. The movement of wind coupled with the shape of structures introduces complex interactions that end up causing uplift and downward forces due to pressure differences. On the other hand, seismic loads are inertia forces that are caused when a structure is subjected to ground motions. Seismic forces develop when the ground moves and the structure wants to remain put. Therefore, structural engineers must calculate the forces that will develop in the structures that they are designing as a result of the ground motions that will occur in future earthquake events. Let us go deeper into how these loads shape our design approach. Each type of load not only acts differently on a structure but also demands a different kind of thinking from the engineer. Some loads are well-defined and straightforward. Others are uncertain, dynamic, and demand strategies that go beyond simple calculations. When designing for dead and live loads, we're working with quantities that are either known, such as the weight of materials, or well-bounded by code, such as occupancy loads. These are deterministic forces. They are fixed, predictable, and applied with safety factors to ensure reliability. The design is straightforward. The role of the engineer is to size the structure to resist known loads with an adequate margin. On the other hand, when we design for earthquakes, we're not dealing with a single force that is known. Instead, we're hedging against uncertainty. We are accounting for a range of potential ground motions and their likelihood of occurrence. Seismic design today is rooted in probabilistic hazard models which estimate the likelihood and severity of ground shaking at a given location based on known faults and historical earthquake data, as well as the geological characteristics that influence the propagation of seismic waves. From this, we assume that buildings will experience varying levels of shaking and may deform and yield under stronger events. Therefore, we are not just resisting loads. We're managing risk by ensuring that even in failure, the structure protects life. The goal is not to eliminate damage in extreme circumstances, but to prevent collapse and to ensure the safety of the occupants. This philosophy of risk-informed design leads us directly to a critical question. What level of earthquake should we design for? For gravity or wind loads, design forces are derived from relatively frequent and measurable conditions. On the other hand, Seismic forces used in design originate from rare, unpredictable events. So instead of designing for one specific earthquake, we design for a statistical threshold. This is the most severe shaking likely to affect a site, based on probabilistic seismic hazard models. The seismic design parameters used by structural engineers originate from the United States Geological Survey's database. These parameters are the result of sophisticated mathematical models grounded in statistical and probabilistic methods. While structural engineers are not required to engage directly with these underlying sciences, they rely on the final design parameters in their work, parameters in which these scientific principles are already embedded. Nonetheless, any structural engineer designing for seismic forces should, at the very least, understand the significance of the seismic design values provided by the USGS. In particular, engineers should be able to explain why the building code refers to these parameters as the risk-targeted maximum considered earthquake spectral response acceleration parameters. This video focuses on this risk-targeted philosophy by tracing its historical development and considering its impact on current design practice. We will see that seismic design did not begin with the current risk-based models. Instead, it evolved through three major stages, with each building upon the insights of the previous one. What began as a purely deterministic approach transitioned into probabilistic seismic hazard mapping, which eventually gave rise to the risk-targeted design philosophy that underpins the current building codes used in the United States. Each stage marked a step forward in our understanding of earthquakes and how buildings should be designed to withstand seismic ground motions. In the early days of seismic engineering, building design was based on a simple but serious question: what's the biggest earthquake we've seen near here? Engineers used the largest known historical earthquakes or the worst-case scenario from nearby faults, which was known as the maximum credible earthquake, to define how much shaking a building should withstand. This approach is deterministic, and it treated the ground motion as a fixed, single-event scenario. While practical and grounded in observable geology, it had serious limitations. It did not account for the likelihood of that event actually taking place. Additionally, this approach was very limited when it came to addressing regions without well-studied faults. The other limitation with this approach is that the risk of collapse did not feature in this framework. It was assumed that if a structure could survive the big one, then that was good enough. Designing for the big one does, in theory, offer protection against collapse. The idea is simple: if a building can survive the most severe earthquake expected at the site, then it should survive anything smaller. But this approach has a major limitation. It doesn't tell us how much safety we're actually getting. It doesn't quantify the risk of collapse or tell us whether we're achieving a 1% chance of failure or something much higher. It also assumes we've correctly identified the worst-case scenario, without accounting for uncertainty in earthquake size, location, or ground motion. And finally, it ignores the possibility of more frequent, moderate events that might still cause significant damage. So, while designing for the big one may hedge against collapse, it does so in a narrow and uncalibrated way. One clear advantage with this method was that it was fairly easy to implement in the pre-digital era. It was computationally manageable since it avoided complex statistical modeling, therefore making it practical for engineers working with limited data and resources. Finally, it provided a baseline understanding of seismic hazard, around which later probabilistic and risk-based methods were developed. Towards the end of the last century, seismologists and engineers began embracing a more nuanced approach that acknowledged the unpredictability of earthquakes. Rather than focus on a single worst-case event, they asked the following question: what is the chance that an earthquake of a given intensity will occur at this location within a building's lifetime? This shift gave rise to probabilistic seismic hazard analysis and the development of national hazard maps by the U.S. Geological Survey. Buildings were now designed for earthquakes with a 2% chance of being exceeded in 50 years, which is an extremely rare but plausible level of shaking corresponding to a return period of 2,475 years. This probabilistic approach brought much-needed consistency to how we define earthquake hazard. It allowed engineers across the country to design for statistically equivalent shaking levels, based on national data. But it had a critical blind spot. While this approach standardized the ground motion, the building's response was largely not addressed. Two structures with different seismic force-resisting systems may be designed to resist the same design acceleration, but Building A would perform poorly and Building B perform well in the same earthquake. The problem with Building A is not the engineer's judgment or design methods, it was a blind spot in the code. It didn't account for how different systems actually perform in real earthquakes. In short, we can say that although the probabilistic approach standardized seismic hazard using a statistical framework, it did not translate that hazard into a consistent or measurable level of safety. The most recent evolution in seismic design shifts the focus from the earthquake to the building's response. In this risk-targeted design approach, the question may be framed as follows: what ground motion will keep the risk of structural collapse below 1% over 50 years? This is the basis of today's risk-targeted maximum considered earthquake. Rather than just considering how often a big quake might strike, engineers now integrate hazard data with structural performance modeling to achieve a uniform level of safety nationwide. The introduction of risk-targeted design did not replace the probabilistic seismic hazard analysis. It refined how we use it. The probabilistic seismic hazard analysis remains the foundation for estimating the likelihood and intensity of ground shaking at any given site. What risk-targeted design adds is a performance lens, a way to ensure that this estimated hazard is not only consistent across the country but also tied to a uniform level of safety. Instead of designing solely for a certain level of shaking, we now design for a target risk of collapse, typically 1% over a 50-year period. This approach builds directly on the statistical principles of the probabilistic seismic hazard analysis and integrates them into a broader framework that also considers how structures behave, not just what they experience. It's important to recognize that these three eras are not mutually exclusive. They represent a progression in how we understand and manage seismic risk. The deterministic design approach laid the foundation, anchored in local geologic knowledge and fault behavior. Probabilistic methods brought in statistical rigor and national consistency, acknowledging that earthquakes are inherently unpredictable. Finally, risk-based design expanded the focus beyond the ground motion to include how buildings behave and how we define acceptable safety in society. Today's seismic design philosophy is layered and integrated. It begins with probabilistic seismic hazard analysis, which estimates the expected level of ground shaking based on where earthquakes might occur and how likely they are. At the same time, deterministic approaches still matter, especially when evaluating critical sites near known faults. But what ties it all together is a risk-based framework that is designed to ensure that even when a building is pushed to the brink, it still protects life. This is the first of many videos that will follow on seismic engineering. Please don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Thank you for watching.